And you know this notation, right? So this is row 2 is 1, 2, 3, and let's say 1, 3, 2. So this is another permutation. And so here, this permutation, there is a way of representing this permutation. Okay, the way of representing this permutation is, so let me, yeah, got it here. Mitansh got it. So 1, 2, 3, and 1, you know, it's we don't consider it. Okay, we just remove this. So 2, 3 is the permutation. So this is this 2, 3 when you have oh, not for ECE students. Okay. So here, this when you have this is 2 maps to 3 and 3 maps to 2. So row 2, this is an alternate representation for this permutation. So this 1 maps to 1. If you just leave it, then whatever that is not in this thing, 1 is there. So we just have this. So similarly here, this is 1, 2, 3, and we don't need to write this because we just we can just leave it as it is, this identity permutation. Okay, let's take one more permutation. Row 3, 1, 2, 3, 3, 1, 2. So what is the representation for this? 1 maps to 3, 3 maps to 2, and 2 maps to 1. This is the cycle representation for this permutation. And then this can be written as what is called as a transpositions, 1, 3, 1, 2. So this is the sign of this permutation is it's a product of composition of two transpositions. So the sign of this permutation is it has an even sign. Someone in the morning asked, what is the sign function? Sign of this one, this is equal to -1 to the power of the even. This is even number, so it is -1 to the power of 0. This is equal to 1. So if you have, if your permutation is odd number of transpositions, then it is then its sign is minus. If it has even number of transpositions, then its sign is positive, 1. Are you with me here? So 2, 3, it's an odd. Like for example, now let's take this one. This one, 1, 2, 1 goes to 2, 1 maps to 2, 2 maps to 5, 5 maps to 1. So this is 1, we write it as, and then we start with 3, 3 goes to 4, 4 goes to 3. So this is product of 2 cycles, but the first one, we rewrite it as 1, 2, 1, 5. So the permutation that we are seeing here, it has odd number of transpositions. So its sign is negative. Are you with me here? Two, 5, it has only, it's odd, only one transposition. So every permutation, it can be written as product of transpositions. Okay, you first write it as product of cycles, and every cycle you divide it into product of transpositions. Are you with me here? Okay. So the point here is now coming to the problem of permanent versus so here if you see the permanent of a matrix is you take, you have a matrix, okay? So the permanent and determinant, you take a matrix, okay? And how many permutations? Sn is the set of all permutations, okay? And there are, you know, there are factorial n permutations possible. The size of Sn is factorial n. So you take a permutation, okay? So that means in the summation of permanent, there are factorial n terms here. Sn, just think of Sn is nothing but set of all permutations. Okay. So now you take a permutation from Sn. You take a permutation. So how many terms are there in this permanent? Permanent of A, how many terms? Factorial n terms, right? Because there are factorial n. And surprisingly, determinant of A is also the same. It looks exactly the same. You look at everything and you say -1 to the power of sign of that permutation into product of AI. Pi is product. I is equal to 1 to n AI sigma. So here, let's say if the permutation, let's look at a permutation which is of this form 1 2 3 3 1 2. So if you take a permutation like this, the value it contributes, the value this sigma, this permutation contributes to the permanent is 1 is mapped to 3. So you take this element, and 2 is mapped to 1. So you take this element, and the third column you map it to 2. So, and you multiply them, G times B times F, okay, G times B times F, you know. So this is the term which gets contributed to the summation contributed by this permutation to the permanent is this. Are you with me? Are you all with me here? There are different permutations. Right now we are looking at, okay, let's do one thing. A, B, C, D, E, F, G, H, I. Okay. Let me start from here. Just give me 1 minute, guys. I'm trying to get hold of the chat box. Okay. I'm going to clearly explain this story. So let's say we are working on a 3 by 3 matrix. So the matrix is this: ABC, DEF, ABCDEF, GHI, ABCDEF, GHI. Okay, we got this right. So now look at the 6 permutations that we have. So 1 2 3. So it gets mapped to 1 2 3. This is the first permutation. Row 2, row 3, row 4, row 5, row 6. 1 2 3 and 2 1 3. This is one permutation. Can you tell me other permutations? 3 1 2 maybe. 1 2 3, 2 3 1. Thank you, Ashma. And 1 2 3, 3 2 1. and 1, 2, 3, 1, 3, 2. Okay, awesome. So what is permanent? Let's look at permanent. So permanent, it consists of summation over all these. Your Sn is nothing but sigma rho I 1 less than or equal to 6. So now you pick a permutation from Sn and we do something interesting. Okay, there is a particular notation here, but what that notation, you can look it up there. But let's say when we take the first permutation, sigma 1, so in column 1, we pick the first element. In column 2, we pick the second element. In column 3, we pick the third element. Okay, we pick the third element. And we take the product of these three. So AEF plus, so this is the product contributed by the permutation sigma 1 to the permanent of the matrix A. And now let's take 2. What is the permutation? 2, 1, 3. So in the first column, we pick 2. In the second column, we pick 1. In the third column, we pick the third element. So the product of this is D times B times I. So this is the value contributed by permutation 2. Plus, now let's come to 3. So column 1, you pick the third element because 1 maps to 3. So because row 3 of 1 is equal to 3. In column 2, we pick element 1. In column 3, we pick element 2. And the product of these three is GBF. Are you following me? What we are doing? So this is contributed by 3. So similarly, if we do, no, so this product will be contributed by permutation 4. This will be contributed by permutation 5. This will be contributed by permutation 6. So this is the definition for permutation. But what is the, but if you want to do the same for determinant of A is defined as, what is the sign associated with the sigma 1? First one is AEI. Yeah, sorry, it is AEI. Sorry. Thank you. AEI. That's true. So what is the sign associated with sigma 1? No, but it has 0 transpositions, right? It is positive. There are no transpositions. 1, 1, 2, 2. There are 0 transpositions. 0 means even. So what happens is for this term will be AEI only. But if you take 1, 2, 2, 1, so this is equivalent to 1, 2. There is one transposition or transposition. So you get DBI. Okay, how about GBF? The third one, 1 goes to 3 for it should be 3, 1, 2. 3 is G. No, I'm saying in term product is same, right? 3B 3, 1, 2. GBF, it's right on. Yeah. So if you look here for 3, then if you count the number of transpositions, it will be 1 goes to 3, 3 goes to 2, 2 goes to 1. This is the 1. So this is 1, 3, 1, 2. So it is even. So what happens is we just put GBF here because the positive. So this is how the difference between permanent and determinant is this. Are you all with me? Okay, 100% pakka. Now the story is the transpositions for sigma 2 is 1, 2 into. No, don't worry about transposition calculation, but there is something called as, there is a way of computing the sign. Can you abstract it away? Because I know I am not explaining the transpositions very clearly. It just takes a bit more time and I'm lazy, and maybe you learn it in some other course. But what I want to tell is there is a way of computing the sign of a, there is a function associated, there is a sign function associated with every permutation. Okay, there is a sign function, it can be plus or minus. And what differentiates permanent and determinant is that sign. Okay, so here every time what we do is number of steps to change back to identity permutation. Okay, so good. So at least can you just take this as an abstract thing, that there is some function which is based on sign, and when we are computing the the difference between permanent and determinant is when we say drop the sign doesn't mean drop the sign in the Kramer's rule for computing determinant. Drop the sign here. Drop, you don't use minus, etc. You just use plus all the time. Are you with me here? Kramer's, or what is that rule? Well, there is some way of computing determinant, whatever it is, I don't remember. Yeah. So what I want to do is understand is drop this in the definition, not in that determinant Kramer's rule. Okay, I don't know about Laplace's method and all, but I just want you to focus here. Are you with me here? Do you see the difference between permanent and determinant? You just abstract it away. Okay, so think of this as some evil person you don't want to think about. Okay, I'm not good at art, some evil. How will this permanent A and determinant A will come out to be the same? It will. How did you compute this permanent A? How did you compute this permanent A? Abhinav? Oh, is it? It cannot be the case. No, I don't know what Wikipedia says. It should not work. Okay, you should write a program and you should check. You write the program for this and you just, okay, take a step back. Okay, just follow my line of thinking and then we will take up the questions. Okay, first thing, do you see the difference between the definition of permanent A and determinant A? Question 1, let's first focus on this. Okay, now it so turns out that you can get this by applying that A11 into determinant of cofactor of element 1, A12 into determinant of cofactor of element, C12 is the cofactor of 1 of the element A12, so on and so forth. This is what? This is not plus, I mean, yeah, so whatever minus. And this is the story which we learn in school. Okay, so computationally, this and this are equivalent with each other. Are you with me? But the problem is you cannot get permanent. You don't have a formulation such as this for permanent. You don't have a formulation such as this for permanent. Are you all with me? That we have a alternate definition of determinant which is computationally efficient. What I want you to see is, if you go to the permanent algorithm, so permanent, there are factorial n terms here. Okay, but on the contrary, in determinant also there are factorial n terms, but there is an alternate formulation for determinant which is computationally efficient. How many of you got this one? That if you do determinant the dumb way, this also requires factorial n. It's very expensive. But there is an alternate formulation, but that alternate formulation is cheap. It is not computationally expensive. You don't need to spend factorial n time. But it so turns out for permanent, there is no such alternate formulation, which is easy to compute. No, recursion doesn't make it cheap. Okay, recursion makes it easy to. Yeah, Tejas got it. So in the permanent question, you need to find permutations using recursion. Excellent. Yeah. Mayank has, we can also calculate determinant by multiplying diagonal elements after applying Gauss-Jordan elimination. Good idea, Mayank. I think it's good idea. Okay. Okay, so no, I'm not sharing my screen now. I will just just give me a minute. Okay, this is the picture which I showed in the morning session. You know the difference between Can you see the screen now? Do you see the difference between determinant A and permanent A? They are just one below each other. So now one thing, so yeah, I will show you one more thing. So the complexity, there is what is called as a polynomial hierarchy. Let me just okay, can someone tell me my car alarm keeps going off randomly? Can someone tell me how to fix it? Sell it, Rohit. No, I am not in car. It just kills me. Randomly, it makes sound. Manual lock. Okay, I tried it. Maybe I went to service center and they didn't do. They reprogrammed it also, not in C. Maybe haunted. Srija. Okay. Have to use manual lock among all the service center. Okay. Give your car, who will reprogram it for you? Will reprogram my car or Take my car for a ride and I'll get a different car or no car. I'm just trying to show an interesting picture. I want to get the right picture. So just give me 1 minute. I was trying to see that. There is only one picture which is reasonable. Just I'm showing one picture, guys. Permanent. Okay, there is one closer picture, and I can try to pretend it is someone else's car, except that car is before my home. So, okay, let me share my screen with you. Yeah. So later on, you should do a course on complexity theory, and you see that the problems are classified into the degree of hardness, how hard they are. Okay. So we call this as, there is one particular classification which is called as a polynomial hierarchy. So you have some set of problems which are solvable in polynomial time. And then there is one class of problems which we call as sigma 1p, another class of problems which we call them as pi 1p. So like that, there is an infinite hierarchy of problems, and this infinite hierarchy of problems, we call it as polynomial hierarchy. Okay. And so while determinant is situated somewhere here, determinant, you can solve it in polynomial time. But computing permanent, it's so, if you can compute permanent, you can solve all these problems easily. Okay, if you can compute permanent, then there is this theorem. Let me do this. Yeah, so there is this theorem which is called as Stoda's theorem. Yeah, so clear all. So there is this, are you able to see my window or the wiki window I'm showing? So what it says is, let's say all of you guys, you are all claiming to solve permanent in, so you have a super fast algorithm for permanent, you're all arguing with it. If you can solve permanent in polynomial time, then what happens is you will be solving some hundreds and thousands of problems from which have been open for years, just like that. You will cure cancer, forget about Nobel Prize, and you will do, there's so many optimization problems, so many difficult computational problems, all of them you would have solved just like that. Okay, so in the morning, you're all arguing with me that you solved all those problems. No, that's what you said. No, you just take determinant to just change the sign and you got the answer. OJ is also saying the same, and you also saying you also got the same answer as what OJ is saying. But if you are able to solve it, then there's a whole, just not one problem, thousands of very difficult and useful problems across so many. You will not be eligible. You will be like superstar forever for the rest. And now, factorial n is not polynomial. It is very, very bad time complex. So you get all sorts of prizes. So all of you would have got all sorts of prizes. We'll be fighting for who should be getting all the big prizes. Turing prize. That is what you are claiming in the morning. No. See, in the morning, what you said, you took determinant, you changed the sign, you got it, na? You used factorial n algorithm for determinant, huh? Really? Okay. Okay, got it. Anyways, the recursion one is factorial n. Okay. Cofactor method is factorial n. I didn't look at the complexity. No, dumb method that we did. I'm just thinking if if it is factorial n. Yeah, I think it could be factorial n because time taken to solve to find determinant of a problem n is, you have a loop, you are solving n sub problems and you are doing some in order to add them up, you are doing some n computations. So because of that, you will get n into. Does this make sense? This function, because we are solving in order to compute n, the determinant. We are solving n minus n. We are trying to compute determinant for n cofactors. The size of each cofactor is n minus 1 times n minus 1. And in order to sum up all the values, we are doing n minus 1 work. So if you expand it, then perhaps it looks pretty bad. Okay. So the method that we did is really bad. Okay. Yeah, approximately n factorial, you can think. It's okay. All right. Great. Yeah, I think, but the way we did it, that it will work for permanent also. Okay, now I see your point. Okay, so if you just do it and then you remove that one, you will still get the permanent. Okay, that's what all of you are claiming in the morning. Yeah? Okay, we can use similar code for permanent and remove. Finally, I see smile on Abhinav's face. That's what I'm telling you, sir. Okay, I think I understood. I understood. Oh, you're smiling from 9 p.m. Good, good, Abhinav. Okay, I see your point. Okay, don't need to. Awesome, awesome. I see, I think the link which, no, one someone gave the similar formulation for perm. You, okay, I see. The method we did still is n factorial and time. Okay. Awesome. I am happy. I learned a lot today because my analysis of that cofactor method, the dumb method that we did, I thought it is polynomial, but when I write the recurrence, it is looking factorial n. So even if you change the sign from minus to plus, for permanent also, it should be factorial n. So yeah, this is the thing that I'm worried because we cannot come up with a polynomial time algorithm for permanent. And I thought the recursive solution algorithm that we have written is polynomial time algorithm. So it makes sense. Okay, hooray. How many of you are with me? Or I am with you this time? You are all okay, okay. Awesome, awesome, awesome. I'm feeling happy and humbled. Good guess, good. I'm very. Then what's the polynomial time algorithm for? No, someone told, na, someone told when we reduce it to some Gauss-Jode, some diagonal matrix, and then you compute the product of elements on the diagonal, some algorithm is there, I guess. Gaussian elimination method. How factorial n? No? Your deadline will be extended. Don't worry. When is the deadline? Thursday, no? I'll extend it. Don't worry. It's okay. I'll tell you. What if someone sleeps at 9? That is the question from Vikram Singh. What is the context though? What if someone sleeps at 9? Nine, if it is 10, 9 is reasonable, no? It's not unfair, I think. 9 o'clock these days. Yeah, maybe. Oh, okay. We have interviews at 12 a.m. Yeah, okay, okay. I see, I see. But you understood why it is factorial and time? Anika asked again. The answer is very simple here. If you look at the code, this is the determinant. So you want to compute the determinant of an n by n matrix. Let's say time complexity be n. There will be n terms in the summation. So, and we have to find the determinant for n minus n cofactors, and the size of each cofactor is n minus 1. And in order to sum them up, all of them together, we approximately do n amount of work. Okay, and if you expand this, then it becomes n into, yeah, you just have to expand this, guys. It's so what happens is, this Tn minus 1, maybe if you write it like this, it is n times, okay, you want to neglect 10. Yeah, you can neglect 10, maybe that's simpler thing. Even if you even if you neglect 10, then what happens is, okay, this becomes T of n is equal to n into Tn minus 1. This is equal to n into n minus 1 into Tn minus 2, so on and so forth. So finally you get factorial, approximately factorial. It is more than, see, factorial n is so large, then whatever the other additive terms that we get will be small. Okay, so now parse is back to form. Okay, you will get all of them by tomorrow. Tomorrow or day after tomorrow, everything will be consolidated. Yeah, TAs are doing it. Okay. Awesome. Good. I think through mistakes, I learned a lot from you today, actually. I was not getting the point you are making in the morning, and only after writing the recurrence, I realized that I'm mistaken. Yeah, I don't need to redo the permanent question. Yes. If you have the, see, my worry was, as I said, if you cannot come up with a polynomial time algorithm for permanent. Okay, if you did it, then then yeah, you don't need to, you don't need to do computer science anymore. You will become world famous, and you make a lot of money, all problems in the world solved. So yeah, it's almost like, yeah, God. So in in computer science, we use this oracles. We use oracles and neat. Weibo is already on flight to MIT. Okay. Okay, then that's all, guys. Anyway, so I will see you on. Yeah, you will get a deadline extension. Don't worry, and I will see you on. Yeah. Today, Thursday. Okay. Okay. Good night. So those of you who didn't eat anything, please do eat something and enjoy. Bye.